Okay, so this is the very, very last video. This is an extra video just to deal with 2 more pages in the notebooklet that have been added on. For the second to last page, I just want to show you visually another way to think about what's happening when you're multiplying complex numbers together. So I've got these 2 numbers here, 2e to the 1i, and I'm going to try to multiply that by 3e to the 2i. And we've seen with Euler's expansion that, one way you can think of 2e to the 1i is that it's like a vector that's too long diagonally, and then it's rotated by 1 radian. Now, just a quick little reminder, Math 12, thinking about radians, how big is 1 radian? A little less than 60 degrees, right? So we can call it 60 degrees to 1 sig fig when we just go to sketch this out. Sure, it's about 57 or so. So this first number that I'm going to try to multiply by a second number, this 2e to the 1i. Remember, okay, just looking back on the previous pages, you could say, 2e to the 1i, that's like a 2 getting multiplied by, and then we've got this Euler's expansion here where we've got cosine of the angle, which is in front of the I, so it's cosine of 1 radian, and then plus I times the sine of 1 radian. So it's been rotated by 1 radian, and it's actually too long. So I'm just going to draw that in red. Remember, 1 radian is about 60 degrees, and this thing is too long. So if I just kind of imagine, drawing something that's at a 60-degree angle, somewhere roughly in here. Now what I want to do is draw something that's too long. Not exactly sure where that's going to put me, maybe somewhere out here. And I want to actually be just kind of sloppy with this, almost deliberately. So maybe that finishes somewhere around there. And I'm just going to draw that in as a little arrow here, saying, okay, this is that complex number. And the size of this diagonal is a 2. And then the angle in here is, remember we saw it like just short of 57 degrees. So this is going to be 1 radian. Okay, great. That's the first number, right? That's this one right here. Now, the next number is longer. It's 3, and it's got an angle of 2 radians. So, coming up on 120 degrees. Probably a little closer to 115. But coming up on 120. And when I say 120 degrees, I mean from 0, which would be the x-axis, we're going to kind of rotate this way, right? So that's the direction that we're going. And this thing is longer. It's 3 long. And so that's probably going to put me somewhere around maybe about here. Oh, get my pen rolling here. Probably somewhere around there. I'm not too worried about getting this exactly right. Let me just zoom in a little bit so we can see what's going on here. I'm trying to draw a number that is 3 long, diagonally anyways. Okay, so if I think about this as like a little vector going like this. And it's got a rotation to it, right? Its rotation is 2 radians, right? As I look back up here, yep, it's got this 2 on that right there. So it has to have rotated by 2 radians, just about 120 degrees. And so that, if I'll find a spot to draw this in here without making too much of a mess. Maybe we'll just change colors slightly here for you. That would go like this. Okay, and that needs to be 2 radians. When you multiply complex numbers together, 2 things happen. We end up multiplying the lengths together. So if we take a look there, we've got a length of 2 and a length of 3. And if I multiply those together, that's going to be 6. So this final number that I'm going to get is going to be longer in this case. And then when I multiply those exponentials together, geez, it's just kind of like doing exponent laws back in grade 9 and grade 10. I'm multiplying powers with the same base. They're both e. Yeah, imaginary numbers upstairs there, but that's okay. I would end up adding those exponents together, so this is going to be 3i, or 3 radians. So if we think about how big 3 radians is going to be, right, it's going to be, let's take a look here, this number but tripled. So we're talking, well, not quite 180 degrees, right, 170 or so, but getting pretty close to 180 degrees. So if I wanted to draw this answer in, it's going to have a stretch to it. It's going to be stretched out, right? It's like 2 multiplied by this one, which was 3 long. So 2 times the 3 is going to be 6. So I'm going to draw a vector that's 6 long, and I'm going to line it up, and I add the angles together. So it's kind of like these numbers, these complex numbers, when you multiply them together, they just rotate. And so I'm going to be drawing something kind of along a line, sorry for that, a line somewhere like this. You know, it's 170-ish degrees, 3 radians, and it needs to be 6 long. So that's going to put me, roughly speaking, somewhere around here. So it's kind of cool that you can think of these multiplications as just being a stretching, where you multiply the size of the numbers together, and then a rotation at the same time. And if you wanted to divide some complex numbers, it's the exact same thing in reverse. You could imagine scaling them back and then subtracting some angle, right? So this final answer here is 6 long, and then the actual angle on it, I'll change colors here again for you. The angle on this is 3 radians. So it's just another different way of thinking about what's going on when you're multiplying these complex numbers together. We're actually just scaling them and rotating them at the same time. Just kind of a neat way to think about it. Now, the very, very last page is actually a follow-up to some work we were doing with partial fractions when we were talking about one option there where you had to, well, not really an option, you had to solve several equations with several unknowns, and there were different options for how to do that. Here's a neat way to do this, especially if you get into 3 equations with 3 unknowns, or maybe 4 with 4, or even, you know, university you might do 5 with 5. You can get your graphing calculator to do this. So I've got a system here of 3 equations. They've got these 3 variables, A, B, and C, and you can see the 3 equations there. I've actually already put the solution here just so you know what we're shooting for, because we're just kind of practicing a way to actually do this. You will take an entire course in university called linear algebra, where you learn that you can take that trio of equations with the 3 variables and then the constant on the end, and you can create what we call a matrix, which is really just a grid of numbers minus the letters A, B, and C. You know, in university, you're doing a lot of stuff, you're in a hurry, and there's no time to be writing down stuff you don't need to, so hey, you could write down this system just as a little number grid that would be 3 for the 3A, 2 for the 2B, a minus 1 for the subtract 1C, and then a negative 45, where you say, yeah, that equals negative 45. And so as a mathematician, we all just have to agree we're going to put them in order, right? The A's first, then the B's, then the C's. So the next one could be a 1 for the 1A, and then a minus 5 for the minus 5B, and then a 2 for the 2C, and then a 151. And then the last one, a 2 for the 2A, a 1 for the B, and then a 3 for the 3C, and hey, that equals 128. So you'll do a lot of work in university where all you do is just draw in these grids of numbers with maybe some little outer brackets hanging onto them. And you'll learn that you can do the same operations that you saw in Math 10. You can add equations together. That just means adding rows together to replace a row, or you can multiply a row by a constant if you multiply everything by it. And your goal is to perform those operations until you get to the pattern that's on the right, which is what we call reduced row echelon form of that matrix. Your calculator will do that for you. It'll go through and add one row with another to make a replacement row. It'll take a row and multiply by a constant, and it'll keep doing that until it comes up with that pattern, if it's possible. All we have to do is add that matrix to our calculator and then ask it to perform that reduced row echelon operation. So here's how you can go and add it to your calculator. You want to go and find the matrix button, which is on mine up above the reciprocal button. So I go second function, matrix, and I can access their names. I can perform some math on them, which I will in a second, and I can edit them. And that's what I want to do first. So I'm going to slide over to edit. I could pick any one of these matrices, and they're a little different than just the 26 memories that you've got in your calculator. I'm going to just use matrix A. So when I go and hit enter on this, so it can fit here when I go and hit enter on this, it says, okay, well, how big do you want this matrix to be? And if you've already got a matrix in your calculator, you can resize it right here. Well, I'm going to type in a 3 for 3 rows, and then I just hit enter. And then a 4 for 4 columns. Now, the TI-84 lets you see the whole matrix. This cheap TI-83 only lets me see 3 columns at once, but they're all there, and I can kind of scroll sideways and see it. And now, all I have to do at this point is just type in those 12 numbers. So I would go in the upper left corner there, a 3, and then a 2, and you can go back. You can use the arrow keys and go back. Now, watch what happens on my cheap TI-83 here. When I go and type in a -1, then it lets me see the last column. I'm like, oh, okay, yeah, there it is, -45, and then it'll kick me down to the next row. I can put in 1, -5, 2, and a 151 for that next equation in that system, and then 2, 1, 3, and 128. Now remember, we already know the answer, right? It's on the sheet there, but we're going to see if we can get the calculator to find it for us. At this point, I'm kind of done editing this matrix, so I'm just going to quit and get out of there. And now what I want to do is ask my calculator to do a reduced row echelon form, right? That's the name for this plan right here. I want reduced row echelon form of matrix A. And so it's going to need to know that request and which matrix it should be working with. So I now go back to the matrix button, so second function, matrix, and I'm going to do some math on it. And there are a whole bunch of different things that you can actually do to a matrix, like find its determinant, transpose it, find its dimension. I want to scroll down until I find reduced row echelon form, or at least an abbreviation of that. And on my calculator, it's this one right here, not the REF. That's just like row echelon form. You want reduced row echelon form. And so I select that, and then it's like, well, of which matrix? Matrix A, but don't just use the alphabet A. You have to use matrix A. So I've got to go back and go second matrix, and there are all the names, and I can just say yes, number 1 for matrix A. Close the bracket if you wish. You say go, you just hit enter, done. Super fast. Now, I'm just going to fill this in over here, and then I'll show you how you basically interpret this. It's got a diagonal set of 1s, and then here's the good stuff. Here's the answer, 7, -12, and a 42. And so the way that you read this, you know, when you see these diagonal 1s here, this is saying, yes, 1A, and no B's, and no C's, is equal to a 7. Right? So that's exactly what I want to know if I want to know A, like how much is 1A worth? And the second row, this row here, says no A's, but 1B, and no C's is -12. Well, that's telling you what B is. And similarly for the last row, no A's, no B's, but 1C is equal to 42. So you can use that, something that could be handy at university if you're trying to solve a system with maybe 4 unknowns and 4 equations. It could be handy. And speaking of things that are useful, especially if you're traveling back east to go to university, you might find that your peers have actually done a little bit of this work already with what's called linear algebra. And I strongly suggest that, especially if you're going back east, that you go to your university bookstore and look for the rack. There will be a whole rack of them of Schaum's outlines. They're like the science version of Cole's notes. And they'll be for all the different possible little topics you can imagine, and they're usually fairly inexpensive, $20 or so, paperback, and grab the one for linear algebra if you need to brush up on that, or for any topic that you feel you need to actually brush up on. So that's something you can buy when you get there. On your journey to university, definitely consider taking all of your calculus notes, throw them in your bag, and bring them with you. You might be surprised how often you want to look for just another resource and quickly look back at some of the stuff we did here at school. All the best, and that ends our very, very last video. Take care.